Good evening, everyone. I am Harshit Agrawal. Welcome to the 12th and the final live session of mine for the week 12 of the course Structural Dynamics CE07. In today's session, we will cover following things. First, we'll just review what was covered in the last live session of mine, that was for week 11 of the course. Then we will just see what was taught in week 12, a brief overview just to brush up the content and get everyone on the same level. Followed by a recap and overview. We will see a series of two questions, each one different from the other, based on the content covered in week 12 and assignment 12. I will first explain you the question and then step by step we will solve the question. So make sure you have a pen and a paper besides you so that you can solve along with me. So, just like the past sessions of mine, I will step by step guide you how to code in MATLAB and we will see the results. So, if you have access to MATLAB, keep it open in your laptop or PC. Else, just write the syntax along with me and we will see and try to replicate it later on. And if any doubts, can ask me through via mail. So I hope everyone are clear with the instructions. If you have any doubts, can raise hand or write your query in the chat box. I will respond as soon as I will see. So in the last live session of mine, that was for week 11, uh, we learned about dynamics of non-structural elements. That are those elements which though won't contribute to the load-bearing functions of a system, but upon earthquake vibration can become critical for damaging the surroundings. Now, earlier, non-structure element didn't concern much to a building, but now, since they form about 70 to 80% of the total building cost, they become critical. Why? Non-structure elements are those rigid elements which don't take up any load, but are a part of a building in different ways, like aesthetics, utilities, and all. These elements So these elements are often neglected by designers during design of a building, but later on can become severe source of damages to mankind upon earthquake vibration. Like even if structure is stable upon under earthquake, these non-structural elements can become dangerous to others. Now, how non-structural elements can get affected due to vibration? There are three possible motions it can undergo. First is sliding, that can happen if force due to ground motion friction due to ground motion exceeds the frictional resisting force. Second is rocking, where a non-structural element will just deform around its base, and this can happen when the frictional resisting force dominates, but the moment due to ground motion exceeds the self-weight moment. And last is toppling, where the non-structural elements will fall down, and this happens when both moment due to ground motion and moment due to self weight both are acting in the same direction as can be seen in the figure. And how to stop these motion? Either by bolting down the base or by tying down the non-structural elements. So, and for these discussed motion, the following table shows the governing equation. These equations are derived using the basic equilibrium conditions of force and moments. But based on these equations, we saw multiple numericals on how to judge whether the non-structural elements will undergo motion or not, and that too which type of motion. We also saw one full-fledged numerical from scratch to solve for motion of non-structural elements. So suppose we have been given a multi-degree of freedom system subject to particular earthquake ground motion, and on each floor there are some non-structural elements we need to check safety for. So how to solve? Firstly, we will form the response spectrum for the given ground motion. This will be done by running two for loops, one changing the time period, and within that, one changing the time step for each time period and recording the responses. And then for each time period, we get the maximum response, and these maximum responses are clubbed together to form response spectrum. So this is something that we have been seen from the week 8 of the course. Post this, we obtain the mass and the stiffness matrix for the multi-degree of freedom system, then solving them for eigenvalues and eigenvectors using MATLAB inbuilt functions. Once we obtain the modal frequencies, we get the most critical vibration period. Now, in general, the most critical vibration period is the first mode of vibration. But if you want to just make sure which is the most critical, we can calculate the participation factor and then we can judge the most critical vibration. Now, once we obtain the most critical vibration, so for this vibration time period, we calculate the earth ground acceleration for each floor, which is generally dependent upon the floor height ratio. So the relationship for that we saw in the last live session of mine, like how a particular base ground acceleration is distributed along the height. Once acceleration is known for each floor, we check the safety of all non-structural elements and provide the suitable precaution for them. So this is how from scratch we solve a system for safety of a non-structural elements. Now, last week, that is in week 12, we learned about damping in the system. That includes classical and non-classical damping and their dependence on structural elements. Apart from this, we learned about damping control systems, which are mainly divided into two categories, passive and active, and focused upon base isolation and tuned mask dampers. The content of week 12 was divided into different modules as in week 12 module 1 we learned about damping, wherein the main focus was on non-classical damping and how to obtain equation for solving it. In week 12 module 2 we learned about vibration control, what is the need for that and different ways in which it can be dealt it with, wherein in this module we saw active control damping working. In week 12 module 3 we learned about base isolation damping, how it works, where it doesn't work, and saw some application where it is being used in India. And in the final module of the week and the course, that is week 12 module 4, we learned about tuned mass damping, how it works and how the calculation is can be done for this. So moving ahead, we will just brush up all the formulae and relationships we saw this week so that everyone can understand the numerical and the MATLAB part coming ahead properly. So just to brush up the basics of this course, the dynamic equilibrium equation is given as inertia force plus damping force plus stiffness force is equal to externally applied force. Assuming that the frame is rigid and deflection can happen only in horizontal direction and the mass of the supporting column is negligible, the actual frame structure can be transformed into an analytical model as shown in the figure. Now, this is something we have been reading since week 1 of this course. From week 2 to week 6, all our discussion were for single degree of freedom system. What are those? And many different techniques to solve the dynamic equilibrium equation for a single degree of freedom system. But in reality, a structure is a complex system which can be seen more accurately as a multi-degree of freedom system since it generally rises up to multiple floor and thus can't be concentrated at a single point. Thus, an actual complex structure can be broken down into a multi-degree of freedom system in which number of floors is equal to number of degree of freedom, and thus this structure with concentrated mass of each floor and known stiffness of the column assuming no lateral buckling or deformation can be simplified into a series of spring block system as shown in the figure in the right. So therefore, we then went on to saw about multi-degree of freedom system from week 7 to week 9, and we learned about eigenvalues and eigenvectors and modal shapes. And then later on, we learned about continuous system and how using generalized parameters it can be converted into a single degree of freedom system in week 10 of the course. And in at last in week 11, we talked about non-structure elements, the discussion about which we have already done. Now, till now, whenever we talked about damping, it was classical damping that is constant throughout the structure. But that doesn't hold true always. Firstly, to be clear with the basics, damping is nothing but an attenuation to the vibration energy of the system. Okay, so it means that when the vibration energy is coming from the ground motion to the system, it is distributed away from the building, or we can say dissipation or attenuation. We have seen in early part of the course several numericals and graph where amplitude of vibration was decreasing with time due to damping, and how with increasing damping the dying of the amplitude was happening at a quicker rate. But what is non-classical damping? It is for non-linear system, or to simply put, when damping factor is not constant, or it can change with the flow height or the vibration frequency, and thus is written to be as a function of u and u dot, u and velocity and displacement. Now, how to define this kind of damping? It is generally seen proportional to mass and stiffness. So the mass offers air resistance damping and stiffness offers frictional damping, and the net damping is given by C is equal to alpha times M plus beta times K. So C is proportional to both M and K, and we write the to remove the proportionality constant, we bring in the constants of proportionality alpha and beta. Now, using the concept of modal orthogonality, the previous equation is simplified, and thus we obtain a final relationship between damping coefficient and natural frequency of the system. Now, in the graph, we see the net effect of frequency change on damping. So, with changing frequency, damping can either increase or decrease. So, it depends critically upon the frequency. After this, we talked about vibration control. Now, what's the need of vibration control? Due to external vibration, when the vibration force are induced in the structure, if the vibration force are very strong, they can cause threat to the structure. And even if the vibration force are not the threat to the structure, it can cause inconvenience to the residents. So there is a need to control the vibration. Now, how it can be done? It can be done by adopting suitable vibration control systems. So these vibration control systems are mainly divided into two categories. First is active damping, in which we tend to comply with the system and completely resist the displacement. And second is passive damping, in which we try to limit the displacement from initial condition, such that the very high displacements are neglected, and only small displacement are happening in the system, which is not causing any harm. Now, in these two categories, we have following techniques. In active control, we have active mass control, active tendon control, and active aerodynamic control. And in passive technique, we have base isolation, mass damper, viscoelastic damper, and friction damper. The two most commonly used are base isolation method and tune mass damping techniques. Now, how active damping works? When there is ground motion, the sensor senses the vibration and sends the signal to a computer, where that vibration is analyzed for its critical nature, and accordingly the structure is updated for increased stiffness. So in the figure you can see, as the ground motion is coming, an arrow is showing where the signals are sending to the sensors. From that sensor we send the signal to the computer, it is analyzed there, and based on the analysis we apply some stiffness resisting members to the structure, tends to decrease the which tends to limit the vibration in the system. So this is something which is known as active damping. Then we have passive damping, in which first is isolation damping. Now, how this base isolation damping work? Herein, below the building, isolation pads are installed, which are generally isomeric rubber pads, which can absorb vibration. What these pads do, they filter out critical high ranges of vibration and allows only non-critical vibration to proceed above in the structure. Between isolation pads, we also have a shear key, which holds the pads and columns above column together. However, now these phase isolation techniques work very effectively, but they are only applicable to small rise buildings and not high rise buildings. Why? because in small rise building there is mainly shear deformation, but in high rise building due to vibration there can be buckling and other motions also, due to which there might be tensile forces in the on the isolation pads. Now, as shear key doesn't take tensile loads, it can deflect from its original position and thus the whole base will rise, which is not desirable. Thus, the application is only limited to small rise buildings, which are generally 5 to 10-story buildings. And finally, we discussed about tuned mass dampers. What is done in this? Additional mass is added to the structure and its frequency is set such that upon ground vibration, it will vibrate out of phase to the actual structure and thus causing destructive interference. What we mean by destructive interference? So, suppose the base structure is vibrating at a certain frequency, the mass damper system will try to vibrate out of phase of that frequency such that the net vibration is getting limited, and this is known as destructive interference, which is causing limitation, which is limiting the net vibration of the structure. So this is how a mass damper will work. We will see a numerical today where where will we design a mass damper system also. Okay, so I hope the week content was clear to everyone. So we'll proceed with the questions now. So this is the first question. The question says a structure to be analyzed is a three-story steel rigid frame as shown in figure. The weights of the floors are indicated in the figure. Assume the width and the depth of the columns to be 40 centimeter and 15 centimeter respectively, and the weight of the column to be 20 kilonewton per meter. Determine the absolute damping coefficient for the structure, assuming 10% of the critical damping for each mode. So I will wait for a couple of minutes for you guys to think how to proceed on with the question, and then we will see the solution. Okay, so let's see the solution now. So what was given in the question? We know a three-story rigid frame structure is given to us. We know the weight of the each floor, and we know the dimensions of the columns and the weight of the column, and the okay. And what we need to determine the absolute damping coefficient for the structure, assuming 10% of critical damping on each for each floor. So herein, first we need to see how we will obtain the absolute damping for each floor. Now, damping matrix C we saw earlier how it is given. It is given by alpha times mass matrix plus beta times stiffness matrix. Now, this damping matrix is coupled matrix. Since K is a coupled matrix, so it's need to be decoupled first. How to do that? By using orthogonality conditions. So we saw in the week 8 or week 9 of this course, when we post and pre-multiply a matrix by model shape, we get a diagonal matrix which is decoupled. So doing the same here also, post pre and post multiplying the matrix by the model matrix, we get the following equation, and assuming the mass term to be mn, will get the following relationship. Now this relation proves that the damping matrix can be decoupled. So this was just for the proof that decoupling can be done. Now, in general, damping matrix is written in the form C matrix is equal to M matrix plus summation of alpha I times M inverse times K matrix to the power I. Now, this is a generalized form of writing a damping matrix. And the first equation at the top that we saw, it is a special case of this matrix. So, this is the generalized form of damping matrix. And when we'll substitute I is equal to 0 and 1, we'll get this matrix. Okay, so this is something special case of this generalized matrix only. Now for any mode shape n, if the damping coefficient can be written as 2 omega and phi and mn, and k times modal shape can be written as omega square mn times modal shape. So when we will use these two conditions and these two relationships, we will get the final relationship. Now this is the critical relationship. Okay, so this is like absolute damping factor for any floor n, and for any mode of vibration n is given by this factor. Okay, so you can easily form a matrix out of this. Phi 1, phi 2, phi 3, phi 4 is nothing but alpha 1 times, if omega is taken inside, so it will become omega cube omega to the power 5 omega to the power 7. So in this way the omega term will vary. Okay, and phi term will be here. So this is how we get the absolute damping coefficient. We'll solve this equation using MATLAB also right now, so it will give you much more clarity. But just to visualize how this matrix will appear, try to write it in a matrix form. Consider a three-story building or a four-story building and write it in a matrix form. Okay. Now, what's the first step before going to MATLAB? It is the defining the system parameters. So, first is mass of the building. Since the building is modeled as a shear building, why we are modeling it as a shear building? Because it is a short building and shear deformation will only prevail it. And under the assumption stated, the entire building may be represented as a spring mass system as discussed earlier. So we can concentrate weight of each floor at a particular point, which will be done as the total weight of the floor plus the weight of column half above and half below. Okay, so the weight of the ground floor will be nothing but the weight 60 kilonewton per meter was the weight of the deck, the slab, the first floor deck, and the half the weight of the columns above and half the weight of the columns below. So it will come out to be 2400 kilonewton. And from that, since its weight mass will be weight upon acceleration due to gravity, so mass will come out to be 2.4 into 10 to the power 5 kg. Similarly, mass of second floor will come out to be 1.3 into 10 to the power 5 kg, and mass of third floor will come out to be 0.65 into 10 to the power 5 kg. And then we'll determine the stiffness coefficient. So we have seen in the week one of the course equivalent stiffness coefficient when the columns are in parallel, it is direct summation. So K1 will be 2 times of 12 EI by L cube. So it will come out to be 67.5 Newton per millimeter. K2 will come out to be 540 Newton per millimeter, and K3 will come out to be 540 kilonewton Newton per millimeter. So this is how we obtain the mass and the stiffness coefficient. Once we obtain the mass and the stiffness coefficient, we can write the characteristic equation for both. We can define the matrix, mass and the stiffness matrix, and from mass and the stiffness matrix, we will solve the characteristic equation to get the eigenvalues and eigenvector. Okay, so now we'll see in MATLAB how we get the eigenvalues and eigenvector. So now I am opening the MATLAB software in my laptop. You can see how to code as of now and implement the same later on. So we'll go step by step and define everything properly and clearly. All the syntax that I will cover today are almost the same that we have covered in the past sessions of mine. So you just need to pay attention. I will try to clarify all of them once again with time, but try to learn more about them from MATLAB official page. And the more you will practice, the more clarity and command you will gain over the things. Okay, so let's see the code now. So this is the MATLAB workspace. Now what's the first thing that we need to do? We need to define the given values. Always try to write comments while coding so that if there are some errors in the code, debugging becomes easy. So first step is to define the mass matrix. Now we have three floors, so we will define all the three masses first and then we'll write the matrix. So M1 is 2.4 into 10 to the power 5. M1 is 2, 4 and 4 times 0. M2 is 1.3 into 10 to the power 5, 134 times 0. And M3 is 0.65 into 10 to the power 5. So 65000. So how the mass matrix will be written? M1 0 0, 0 M2 0, 0 0 M3. So M1 0 0, 0 M2 0, 0 0 M3. Now we will define stiffness matrix. So for this also we'll define K1, K2 and K3 and then we'll write the matrix equation. So K1 is given by 67.5 Newton per millimeter. We need to convert all the units in the same order. So we will convert it into Newton per meter. So 67.5 into 10 to the power 3. So 67500. K1. K2 will be given as 540 into 10 to the power 3, 540000, and K3 again is 540 Newton per millimeter. So it is 540000. Now we need to write the stiffness matrix. So stiffness matrix is given by K1 plus K2 minus K2 0 minus K2 K2 plus K3 minus K3 and 0 minus K3 K3. So K1 plus K2 minus K2 0 minus K2 K2 plus K3 minus K3 0 minus K3 K3. Now we have defined both mass and the stiffness matrix. So the third step will be to solve for eigenvalues and eigenvector. Solve for eigenvalues B and eigenvectors A. So for this, we'll use the inbuilt function of MATLAB, EIG function. So it will be given by A comma D is equal to eig K comma M. Now, what this matrix will return? So A will be eigenvalues, eigenvectors. So it will be like a 3 cross 3 matrix representing the deformation of each floor for each mode of vibration. And D will be eigenvalues. So these eigenvalue will be again a 3 cross 3 matrix, diagonal matrix. So along that diagonal, we will have the eigenvalues. So eigenvalue is nothing but omega square. So we will get the natural frequency. Now we can even visualize how A and D is appearing. So this is A matrix and this is B matrix. So you can see in first mode of vibration, all the deformation are along the same direction. In second mode, one deformation is changing. So there is one time change in direction, and in third mode of vibration, there is twice the change in direction, which you generally observe. And D matrix is a diagonal matrix. Now we will obtain. So step 4 will be to obtain natural frequency. So we'll obtain natural frequency. We from the solution we may or may not get the sequence, right sequence of natural frequency, the mode of vibration. So to do that, we'll use the sort function as well. So omegas comma k. So omegas are the natural frequency and k is the order, first mode, second mode, and third mode. So it will be sort sqrt times diagonal d. So with diagonal D, we are getting the diagonal values of the matrix. We are doing square root, so we get the omega, and we are sorting that matrix so that we get the right sequence. So let's see what we have obtained. So omegas. So these are the three natural frequency, and what is the order of this? So uh, omega is equal to 0.3883 is for the first mode of vibration, 2.1008 for second mode of vibration, and 3.8187 is for third mode of vibration. Now we'll see the eigenvectors. Okay, so we'll arrange the eigenvector also in this same sequence. For now, the sequence is the same of what we obtained, but still we need to know how we can rearrange the eigenvectors if the sequence is not in the particular order. So rearranging eigenvector in modal order. How to do that? A is equal to A comma K. So this will arrange it in a particular order. Now the next step is to obtain the natural period. So natural periods. So natural period will be given by 2 pi by omega. So 2 pi dot divide omega. So why we do dot divide? So that since omega is a matrix, is in matrix form, so it will divide each term by 2 pi, multiply each term by 2 pi. Um, sorry, it can't be zoomed anymore. It is of the maximum zoom only. Wait, no, it can't be zoomed anymore. Just try to listen the code right now. You can later on pause and replay and see. Okay, so natural period is defined by,
Sir,
yeah.
I think the control plus the mouse scrolling should work. Can you try that in the MATLAB screen?
Okay, I will try. No, it's not working in MATLAB.
Okay, okay, okay. Thank you.
You just try to listen to the code right now and you can later on see. I have attached the syntax of the code in the slide also, so you can view it later on also. The syntax will be there in the slide, so you can see the slides later on. The slides will be made available to you. Okay, so where we were we have defined the natural period. Now the next step is to get the orthogonal matrix. So it is like model shape transpose into mass matrix into model shape. So that we do for obtaining the Q matrix later on. So the next step is to step 7 is to obtain orthogonal mass matrix. So AMA, we will denote the matrix by AMA is given by diagonal of A transpose times M times A. Okay. Now why we are doing this? We need to see the syntax. So this was the orthogonal matrix that we are forming now. So that will be used here on for calculation. Okay. Now we need to define the damping ratios. So this is something that we need to define. This is given to us 10% for each flow. So once we have defined this and we know the value of this, we can obtain the alpha E value. Once we'll get the alpha E value, alpha, beta and gamma, we can substitute the alpha E value here and we'll get the absolute damping coefficient. So I hope I'm clear with the flow. We know the damping ratios for each floor, sigma n, which is given as 10% of critical damping, and we have obtained the natural period. Okay, these two things are known. We need to calculate the alpha, beta and gamma. So this is something which is deconvoluted. Okay, once we know the alpha, beta and gamma, we'll get the absolute damping matrix. So we'll see how to code for this now. Okay, so step A is to define damping ratios for each mode. So for this, let's first see the what is the size of the matrix. Right now we know it is 3 cross 3 matrix, but how it can be done through code, just use size matrix. Now we'll define the zeta matrix, the damping coefficient matrix as zeros n comma 1. So we are defining the LHS. Okay, so we know zeta for all three floors are the same. So zeta's 1 is equal to zero point 0.1, zeta's 2 is equal to zero point 0.1, zeta's e is equal to zero point 0.1. Okay, once we have defined the zeta matrix, what's the next step? So we have defined this matrix. Now what we'll do, we'll define the omega matrix. So it is nothing but when n will be equal to 1 and I is equal to 1, so it will be omega square, omega to the power 4, omega to the power 6, and 1 omega is outside, so it will become omega, omega cube, and omega to the power 5. So first will be omega 1 cube, omega 1 to the power 5. Second row will have omega 2 cube, omega 2 to the power 5, and third row will have omega 3 cube, and omega 3 to the power 5. So when you will write this equation in the matrix form, you will obtain the relationship that I have just said. So I will just write that relationship. We will define that by q. So q is nothing but omega's 1 first mode of vibration, omega's 1 cube, omega's 1 to the power 5. So this is first row. Similarly, second row will be omega's 2, omega's 2 cube, omega's 2 to the power 5, and third row will be omega's 3, omega's 3 cube, omega's 3 to the power 5. Okay, so first row is for first mode of vibration, then for second mode of vibration, and then for third mode of vibration. You can see this how the Q matrix will appear. Now, how we'll obtain the A alpha beta gamma? So alpha beta gamma will be nothing but epsilon n into 2 into inverse of Q. So when this matrix will come here, it will become Q inverse. So Q inverse into epsilon n into 2. So we can write it directly. A is equal to, or I will write as an alpha matrix is equal to 2 times inverse of Q into zetas. So these are the alpha value. Now how we'll obtain the damping matrix? It will be nothing but mass matrix we know, alpha I values we know, and we just need to write this equation for I is equal to 1, I is equal to 2, and I is equal to 3. So I is equal to 1, it will be nothing but alpha. This term will be nothing. First we will write this term, and then later on we'll multiply it by mass. So let's say the inner term is AMK. So it is nothing but A1 alpha matrix 1 times inverse of M into K plus alpha matrix 2 into inverse of M into K square plus alpha matrix E into inverse of M times K cube. So this is how we'll get the AMK matrix, and to finally get the damping coefficient, we'll multiply it by the mass matrix. So E into AMK. So these are the damping coefficients. So this is for first mode of vibration, this is for second mode of vibration, and this is for third mode of vibration. Negative sign is just showing the direction, I guess. So it doesn't mean anything. You can have take the absolute values of these things, and you can also define the normalized value. If you want to define the normalized value, just multiply the damping matrix by post and pre-multiply damping matrix by the normalized matrix. We have seen how to normalize the model shape before, so you can do that on your own. So this is how we obtain the absolute damping coefficient for each floor. I hope the code was clear to everyone. So first we defined the mass and the stiffness matrix, then we obtained the eigenvalue and the eigenvector. From that we got the natural frequencies. Once we got the natural frequencies, we defined the orthogonal mass matrix, and then we defined the eigen matrix and the omega matrix, and then we calculated the constants of proportionality, and using the constant of proportionality and the known and the mass and the stiffness matrix, we got the absolute damping matrix. So this is how we solve for absolute damping matrix for non-classical damping system. If there are no doubts, we'll proceed ahead now. So this was the omega value that we obtained, and this is how do you normalize. So when you will normalize, you will get these deformation values. So these normalized matrix, if you will multiply, you will get the normalized damping coefficient also. So you can do that on your own. And this was the first mode of vibration, frequency for first mode of vibration, second mode and third mode, and how the modal shape are looking. So this is what we discussed also. And this is the code layout for the question. So if the code was not visible clearly, you can see the code here also later on. So let's proceed on with the second question now. So the question says, consider a single story building as shown in the figure. The tuned mass damper needs to be designed for the given building for no damping condition. Determine the parameters for the tuned mass damper. Assume E to be 200 GPa. So I will wait for a couple of minutes for you guys to think how to solve this question. We need to design a tuned mass damper system here. So I will wait for a couple of minutes and then we'll see the solution. Okay, somehow the connection was lost. Okay, so we are discussing the tuned mass damper system question now. This is the question. I will wait for a couple of minutes and then we'll see the solution. One final question left. हाँ पता नहीं, मैंने ध्यान नहीं दिया. आज वाला मैटलैब कोड थोड़ा क्रिटिकल था, तो उसको समझाना बहुत टेढ़ी खीर थी मेरे लिए. बस एक क्वेश्चन और है, वो टाइम पास वाला क्वेश्चन है, क्योंकि 7 बजे तक कुछ तो पढ़ाना रहता है ना, तो एक और क्वेश्चन डाल दिया मैंने. मेन चीज़ तो हो गई कंप्लीट. आज ही सब अपलोड करके ख़त्म करना है, वो सर्टिफिकेट कल दे देंगे. फिर मैं एक व्हाट्सएप स्टोरी डालूंगा. फाइनली डन. एक क्वेश्चन और बचा. अरे सब खुशी एक साथ आ रही है. स्क्रीन गार्ड नहीं लगा रखा है तूने? खुद ही निकल गया. चल अब मेरे को पढ़ाने दे. Okay, so let's see the solution now. So what is given in the question? We have been given a single story building and we need to define a tuned mass damper system such that there is no damping in the system. Okay, and we know the width of the columns, the length of the column, the weight of the first floor deck. So as seen in the first week of this question, if we make two assumptions, the mass of the columns are neglected and the horizontal member is sufficiently rigid to prevent any rotation on the at the top of the column. If these two conditions holds true, then the system can be analyzed as a spring block system with mass m and stiffness k. Now, first step is to determine the system parameters. So the weight of the frame is 0.5 kg per kilonewton per meter. So it will be zero point 0.5 into 10, 5 kilonewton. So the mass will be weight upon acceleration due to gravity. It will be 5 into 1000 divided by 10. So 500 kg will be the mass. And the stiffness of the columns, it will be given by 12 EI by L cube. So I is BD cube by 12. It will come out to be 9216 millimeter to the power 4, and E is given in the question 200 GPa or 2 into 10 to the power 5 MPa. And the equivalent stiffness will be summation of both the columns. Since the columns are invalid, so it will be twice the stiffness of one column, so 2 times 12 A by L cube, so it will come out to be 2.381 Newton per millimeter. And since the stiffness and mass is known, the natural period of frequency will be under root of k by m, so it will come out to be 2.38 radian per second. Now, second step is to design the tuned mass damper element. So let's assume that the mass of the damper is 10% the mass of the original body. You can assume the mass of the damper from 10% to 30%, anything. So the mass of damper will come out to be 50 kg. So as per the relationships that were defined in the course, the optimum frequency will be given by 1 upon 1 plus gamma. Gamma is nothing but the mass ratio. So 50 upon 500, that is 10% only. So F optimum will come out to be 0.909, and epsilon optimum will come out to be under root of 3 gamma upon 8 times 1 plus gamma. So it will come out to be 0.0341. Now what these optimum values mean? So when the frequency and the damping coefficient of the damped mass system will be these values, then the net vibration in the structure will get minimized. So this should be the frequency and the damping factor, so that the destructive interference takes place and the vibration gets minimized. So for satisfying these parameters, the damper element should have stiffness and damping coefficient of following values. So k optimum will come out to be gamma k times f optimum square. So it will come out to be 0.3234 Newton per millimeter, and damping coefficient will be given by 2m omega naught epsilon optimum into gamma, and it will come out to be 8.11 Newton per meter second. So with these values, if we design the damper mass, the net body will vibrate with minimum deformation. So this is how we design a tuned mass damper system. So if they are a multi degree of freedom system also, then also we can define the tuned mass damper system having known value of frequency. So for that, we will take the most critical frequency of vibration, either by considering the first mode or by calculating the participation factor, and then we'll design the tuned mass damper element. So this is how we define. This was the solution for this question, and that is all for today's lecture. Any doubts in the question? So I will be there in the meet available till 7:30. If you have any doubts, you can ask. Then मेरा काम करते हैं.